Good, we've got an interesting evening for you tonight. We're now on week 8, so we're kind of making progress through the course here. We have 4 sessions left. And this evening we are going to be talking to you about more on testing, aspects on the design of object-oriented systems, so-called solid principles we're reviewing. And I think you'll be also interested to learn a little bit about your next assignment. The assignment is posted in the assignment section. I'm taking you to it here. And we have assignment 2 specified, just went up this afternoon. As you know, this module has 2 assignments. You've done one, really good work. I'll talk a little bit more about that later on, but myself and Siobhan had a good time going through them. And we were very impressed really with what you're doing. I think there's a lot of learning going on. So we're looking forward to the second one and what you think of it. It's very much going to build on the first one. So a lot of the work you've done, you get a chance to revisit some of your strategies, but also we'll try to push it into some new territory as well. We'll talk about that then maybe as our third talk this evening. So week 8, we're revisiting testing again. We're looking at, in general, what makes, or how do we judge higher quality design of a system? And then we'll talk about the assessment itself first. So I'm going to kick off now with the first talk here, which is what we're calling one of the correct suite of principles for testing. Now you've been involved in unit testing now for a couple of weeks, I think. You did a very good job on the tests in your assignment. And you've been through a range of labs that are starting to ease you into this way of thinking about software. We introduced tests and the concept of test-driven development. You wrote some initial tests. And then we started to explore some examples in a bit more detail, particularly the stack and video player we looked at a few weeks ago. Here we were starting to tease out how you would go about thinking in a test-first mode. Sometimes we talk about being test-infected. It sounds a bit weird, but the idea is that you become almost addicted to writing tests. And you regard no class as complete, really, without a suite of tests to exercise the class fully. I think Siobhan explored the right bicep suite of guidelines with you a few weeks ago, which started to take you into specific things to look at, or specific ways to think about your class as you're writing your tests, or more specifically, specific strategies to apply in formulating tests. So that's the spirit of this review here. We're calling it correct thinking. Again, it emerged about 10, 12 years ago. This type of thinking worked out in the famous text pragmatic unit testing and significantly revised in recent years. Correct is an acronym for, we might call them dimensions around which we consider boundary conditions in a system. Conformance, ordering, range, reference, existence, cardinality. And the idea is that errors often lurk at the boundaries. And if we're contemplating the boundaries, we need to be fairly thorough in what we regard as a boundary. And we try to recognize the multiple dimensions associated with this. And correct thinking is all about what can go wrong, and also perhaps what else can go wrong. It's a kind of a Murphy's law of software development. And we're all the time looking at questions really we could pose in the form of tests of the system under test that we're constructing. So let's take a look at each one of these in turn for a few minutes, look at a small few examples, and some are fairly obvious, some a little bit more surprising than you might think, and some common pitfalls as you proceed. Conformance is probably the one you're most familiar with. A class system is expecting some information, perhaps from a user. Does the information conform to a specific standard that we're expecting? And the classic one is emails. You've already taken some experience of this, I think, in your assignments, and some of you were doing email validation checking, which is interesting. A valid email is fine. What if the email is valid, but is perhaps not quite in the format that we normally use, so multiple domains. What if there is some unusual separators in the email prior to the @ symbol? And of course, what if it's completely off base? We would be, of course, expecting our application to respond sensibly to all these, and we could encapsulate those responses in tests in advance of any deployment. We wouldn't be waiting for users to type these in fields. We would be fully exercising in our unit tests a range of these values. That's easy enough. Ordering, we've already come across this. If the system we're building has some ordering relationship among it, does that precise order have a possible influence on the algorithm? And we saw this in a fairly early example, whereby if we change the order in which the data we were provided, it did surface subtle bugs. So if a sort routine has got to be triggered, or if the data is already sorted, what if it's sorted in precisely the reverse order? A search routine, what if the search target is the first or last element in the search data set we're interrogating? First and last is often a position in which errors occur and may be possibly ignored by a naive search algorithm. Range is a little bit more subtle. If our system has types that seem to be subset of primitive types, particularly numbers, then it may be worth considering encapsulating a range somehow to isolate the sub-range that is relevant or valid for our particular use case. Bearing is an example. Say bearing is 0359, it's a compass bearing. We could just represent that in ints, or we could introduce a bearing type to encapsulate the int, and then fully range check that encapsulated type in our class. Maybe trying exceptions, though exceptions mightn't be the best idea. This could mean our tests are exercising that bearing or that specialized range type with fairly obvious tests here to see are we using it correctly. If the range type then can be demonstrated to be secure, then we can use or deploy this range type in our application as a whole, and of course continue with our testing regime to verify that's being used correctly. Reference, this is the second R in a little acronym here. Consider to refer to external dependencies, referencing something outside the scope of our application. Perhaps not our application, but perhaps out of the system under test. And particularly, what happens if the state of the external system varies? How does our test respond to that? In particular, how can we simulate this type of exceptional condition in our application? This example here, looking at perhaps an automatic drive in a car. The test is very simple-minded now. But we're looking here at some essential assumptions about the state of the objects we're interacting with, transmission and the car itself. If we're in drive and we accelerate, then we should still be in drive after we've accelerated. If we're in drive and we accelerate and then we go to park, then we shouldn't really shift to park immediately. We should be staying in drive. So we're deliberately forcing a severe error here on the system, and we're expecting it to behave sensibly as a result. If we are in drive, we accelerate and we stop, then we should be in park after we shifted to park following a break. It's a little bit subtle to see the point here. The point is that references to external or parallel systems should be explored to see how they affect and respond to stimuluses we're applying to them. In particular, we're looking for exceptional sequences of events and how our system under test responds to those and responds appropriately. Existence. This refers to perhaps a more easy to cope with notion. We're relying on systems that are outside the scope completely of our application, perhaps network resources, perhaps files on a remote server, perhaps URLs. What happens if they disappear? What happens if the network goes, obviously? What happens if we provide null, zero, or empty as references to any of these external entities? Again, our tests could consider these in detail and respond in an orderly manner to the absence of resources existing in the scope of our application test. Cardinality, this is a kind of a fun one. Fence posts. You've got to erect a series of fence posts along 12 feet distance, and you want 3 feet between each post. And the question is, how many fence posts do you need? Normally, you might be tempted in your head to say, yeah, 12, 3, 3, 12, 4 posts. Yeah, let's go with 4. Of course, you know that's not the case. It would be 5 if we're to get 3 feet and a post at either end. And that's a very common human error. It's so common, it's got its own Wikipedia page. Worth having a look at that link there on the slide. They're called off by one errors. And off by one errors are notorious really in software. They often revolve around loops, maybe -1 as the boundary instead of 1, or sorry, instead of length, or a length +1 not being checked correctly. You can see how it could happen in different languages. Another aspect of cardinality ties into what's called a 0-1-in rule. If we've got a dedicated facility to manage a specific number of things like 10 or 100 or 1,000, then very often errors can occur at exactly the boundaries or at 1. So a test would test for 0, a test for 1, and then test for some large number. If there was a boundary, you would test for the large number itself. So if you've got a top 10 list of items, let's say that's part of the requirements, then you would need to test for 0, for 1, for many, and for 10. And these might be separate set tests. And you've seen evidence of that, I think, in some of the tests we've assembled as you've proceeded through the some of the labs. 0-1-in rule. Time, then the last one. Again, you've had some fun with time and time formatting, I think. It's quite a challenging thing to incorporate times and durations into any piece of software, and that's why we inserted it into the assessment, just to give you a feel for that. When we're thinking about testing and the impact of time on the security and robustness of our application, we might talk about relative, absolute, and then a very large issue is concurrency. Relative relates partly back to the existence criteria we're looking at. The order in which things happen can be important. Login must be occur before logout. What happens if you call logout before login? Prepare before execute or connect before read. Again, we all know the inherent order in which these things could happen. Part of being obsessed with tests is to deliberately provoke out of sequence events and observe and make the system robust to those out of sequence events. Absolute time is a slightly different dimension. You've been dealing with aspects of that in the assignment. Computing durations, for instance. computing handover times or boundary times. A kind of fun question again, this last one here. Every day has 24 hours, true or false? Apparently it's not true. Who knew? UTC is GMT, it's true. If you don't have daylight savings time, it's true. However, if DST is used, and we use it in Europe and in the United States, there is a day in the year when there are 23 hours, and there is another day when there are 25. In fact, early versions of Java had a problem with this, and there were a couple of attempts to get it right in terms of the time libraries, and emergency patches issued from time to time. Perhaps we'd hardly be seeing in our applications evidence of this particular condition, but it is a notorious source of errors. Concurrency is the final one, and this one is kind of beyond the scope really of what we're exploring. If our application has multiple threads, what happens if our data structures are interacted concurrently at the same time? This is this is a major issue really, and the whole issue of concurrency is very much tied to the language model and how the language may support concurrent access. Java has a particularly sophisticated variety of ways of dealing with concurrency. But of course, in many contexts, the advice is to not do it. That is, don't do concurrency and rely on frameworks that isolate us from it. Testing concurrent applications is very difficult, and it's probably a stretch to say that unit testing has much to offer in this realm. That's an overview then of another suite of testing, I won't say folklore, but perhaps rules of thumb to consider. Part of these idea is that some of these are internalized into your strategy as you're evolving the class, and combined with other rules of thumb that we've covered in the past and we'll cover in the future. They give us some, I think, interesting insight into the range of complex conditions that can occur in a running application, and how far we can start to simulate some of those in our tests obviously contributes fairly significantly to the robustness of our application. We're not really finished with testing yet, and Siobhan will be talking to you again next week about more testing strategies. And we'll probably keep talking about testing until the end of the course itself. But that's it for the moment on this particular topic. I'll take a little pause now for a few minutes, and then we'll come back and we will continue on with our introduction to a new series on solid principles.